Okay, so we talk about the pumping lemma for context free language. So, it is a we know the pumping lemma for regular language. So, that is a necessary condition to be a language to be a regular. Even using that, we have seen many languages non regular. So, that is a good way to prove that a language is not regular. If a language is not regular, pumping lemma will help us to prove that, because this is a necessary condition. So, similarly, we have a version of the pumping lemma for CFL. So, let us define that. So, this is the statement, let L be a CFL context free language, then there exists a N. There is a constant N depending on only on L such that if we take a z in L whose length is more than n, if we take a z in L and length of z is greater than n. Okay. This is very similar to the pumping lemma for the regular language. Then we may able to write z as u v w x y. These are all strings coming from that input alphabet, such that we are going to pump here and here, such that these two should not be, I mean epsilon, that means I will write that, such that three condition is satisfied, such that this V x should be greater than or equal to 1. So, they are, that means they are not a null string, V x is not equal to epsilon, they are not a null string, because we are going to pump there. And second condition is V w x is less than or equal to n. Okay. This part is less than or equal to n. Then we have this like then this is the condition, necessary conditions, that for all I greater than or equal to 0, we can pump there. I mean u v to the power I, u v to the power I, w x to the power I, y, this belongs to L. This is for all I, including I is equal to 0. If I is equal to 0, this won't be there, u w y will be there, but if I is 1, that is our z, if I is 2, that is this is the very similar to the pumping lemma of the regular language what we have. We can pump there. Okay. So, yeah, so this is the statement. The proof will be there in the lecture note. I am not going to discuss the proof in the class. Proof is little tedious, like this n is basically, if we draw the tree with the number of, this is a CFL. So, you have a number of variables. So, 2 to the power of n. So, if you draw the tree of parts tree, so that is the how much it is, maximum size is 2 to the power of L. So, that is nothing but our this n. Okay. So, proof won't be there in your syllabus for the exam. So, this is the statement. So, now using this we can so many language which are not regular. So, in short we can write this. So, if L is CFL, then there exists a n such that if z is greater than 0, z belongs to L, and then z will be written as u v w x y such that this is greater than 1 because this should not be epsilon and this is less than n. V w x is less than equal to n and total is greater than n, and then we can pump there. Then this is telling us this is the necessary condition. Then u v to the power I w x to the power I, we are pumping in x string, v string and x string y. This will be belongs to L for all I greater than equal to 0. For all I greater than equal to 0. So, this is what is called pumping lemma for CFL. Okay. So, now we will use this to see some language which are non-CFL. I mean, so let us take one example where we take a language and we prove that it is non-CFL. So, for that we will use this pumping lemma. So, this is the applications pumping lemma of CFL. Okay, so how to? So, we will check whether certain language are regular or not. For example, if you take a language like this 0 to the power n, 1 to the power n, 2 to the power n, or a to the power n, b to the power n, c to the power n, anything where n is greater than 1. Is this a CFL? No, this is not a CFL. This is not a CFL. We have to, but we have to prove that. So, to prove that we will use pumping lemma. So, what we do? Suppose this is a CFL. Let us assume this is a CFL. Suppose L is a CFL. This is the assumption and we will reach to a contradiction. So, if this is a CFL means there exists some n. Okay, we take this m, say, other is this m and this n will be confusing. So, there exists a n which is in the pumping lemma that such that if we take a z in L and if you take mod of z greater than equal to n. So, if you take just z equal to 0 to the power n, 1 to the power n, 2 to the power n. So, what is the length of this? 3n, 3n is greater than n. So, this is our z. Now, this z will be written as u v w x y, where we have all the properties like v x is not equal to epsilon. So, that means this is greater than, length of this is greater than 1 and v w x length is less than n. Okay. Now, since this length is less than n, yeah, so we have to argue here, to make the argument over here. Okay, so we are taking this. Now, now the claim is VWX, this part, this cannot involve both the zeros and 2's. This cannot involve this cannot involve both zeros and 2's. Okay. Why? Because this is less than n, if it is has to involve 0. So, this is basically 0 0 0 n times, then 1 1 1 1 n times, then 2 2 2 n times. Now, if you have to involve 0 and 2, then this will automatically come in the middle. So, there this will create the length more than n, but we are taking this u v x is less than n. So, it is either involving 0 1 or involving 1 2. So, that means u v w is either zeros or ones or ones or twos. Okay. So, if it is zeros or ones, so that means u v w is coming from here. So, that means and they are less than n. So, the v and so that means v and so this u v w v w x, they are basically coming from this 0 to the power n 1 to the power n or 1 to the power n 0 to the power n. So, if they are coming from this and their length is less than n, so we have few part over here, few part over here. That means, the v will consist of zeros, v is only zeros and x is only ones. Okay. So, that means, v is some 0 to the power l and x is some 1 to the power k, something like that. Okay. So, that means, what is u? U will be, so what is u v w x y? U v w x y is 0 to the power n, 1 to the power n, 2 to the power n. So, this is basically, this will be written as, so u, so 0 to the power. So, even we can have mixture also. So, that means, it is basically 0 to the power u 0 to the power n minus l, then v, then w, and then x. X is 1 to the power k and then 2 to the power n, something like that. Okay. So, now we know that pumping lemma is basically what it is telling. Now, if this is this, then u v to the power I, w x to the power I, y, this will also belongs to L. This is the necessary condition for all I greater than equal to 0. Now, if we put I is equal to 0, then it will be like this. So, this part is gone, this part is gone. So, then it will not be of the form 0 to the power some p, 1 to the power p, 2 to the power p, it will not be this form. So, that means, even for I is equal to 0, this will give us u w x, this does not belongs to L, because this is not of this form, sorry, this. So, there is a contradiction. Contradiction means, this has to be belongs to L for all n, all I, we are pumping there. So, this we reach to a contradiction, that means, our assumption was wrong, that means, this cannot be a regular language. Okay. So, this is one example, we may have another example. So, I will take another example, but this proof is there in the lecture note for other example. I will just state that. More examples. We can prove using pumping lemma similarly. If we take a L like this, x belongs to such that mod x is a perfect square. This is not a regular. So, this is proof will be there in the lecture note. So, even a to the power I, b to the power I and c to the power j, a, b, c are alphabets, where j is greater than I. This is also not regular. So, all these we can prove using pumping lemma. A to the power I, b to the power j and c to the power k, such that I is less than j less than k. Okay. So, these all we can show this not a regular language. Even this w yeah, WW. So, this is say WW, same string, I mean W is coming from is not regular, not CFL, sorry. So, these all we can, so they are not CFL. Many others example are there, this will be given in the lecture note, even using the 4, 5. So, these are all example will be there in the lecture note. Now, we are going to use this property to show that given two regular language, their intersection is may not be regular. So, we have discussed this closure properties of CFL, closure properties of CFL. So, we have seen if we have two L1 L2 CFLs, then we have seen that their union is CFL, their intersection their concatenation is CFL. Now, we will see whether their intersection is also CFL or is not. So, intersection is not a CFL. So, CFL is not closed under intersection. So, that we will see. So, are not closed under intersections. Okay, so for that we take a language L, a to the power I, b to the power I, c to the power I, where greater than 1. So, this language over a sigma ABC. Now, we can show this language is not regular using pumping lemma. Is not a CFL. Using this we can easily verify. Okay. So, these properties this we will use. So, this the intersection is not a CFL. Now, so this this is we have to see this language is the intersection of two CFL. So, how to see that? So, we take two language L1 which is a to the power I, b to the power I and c to the power j, where I is greater than 1 and j is greater than 1. And if you take another language L2 which is a to the power I, b to the power j and c to the power j, where both the I and j are greater than 1. Now, we can just check this L is nothing but L1 intersection L2. Okay. Then we have this. Now, the question is, so this is L is intersection. Now, these two are CFL. How to prove that? So, to show that we need to create a grammar. If a CFL means we have a grammar which can generate that, we have a context free grammar which can generate that. So, let us construct a grammar for this L1. So, we can construct a grammar for L1 like this. S is going to AB and A is going to AB or AB and B is going to CB or C. So, this is the grammar for L1 and what is the grammar for L2? S is going to CD, capital C is going to AC, capital C A and D is going to BD small c and BC small c. So, this is the grammar corresponding to L2. Okay. So, then we can so this two are CFL because we have a CFG on CFG which is CFG, which is G1, and we have another CFG context free grammar, which is G2, which is G1 is generating this, G2 is generating this. So, that is why these two are context free language. And once these two is context free language, then we can, their intersection is this one, but this is not a context free language. So, that is why this is not a context free language, you can see using the pumping lemma. So, the intersection, this is a counter example where we have seen the intersection may not be a context free language always. Okay. So, this is one example. Now, we will see the complement. We see the complement, whether complement can be a context free language or not. So, so the CFL are not close under complement, are not close under complement. That means, given language whether the complement is also a CFL or not. So, that means, if L is a CFL, which is coming from this say, then L complement or L bar, is this a CFL? This is CFL. Now, the question is this a CFL? Answer is again no, and again we can justify this using the this intersection property. So, complement, for complement what we can do, suppose L1 and L2 we have. Now, L1 and L2 intersection we can see as a L1 complement union L2 complement, then whole complement. Now, if we assume that complement is close under if we assume the CFL is close under complement. So, if L1 is a CFL and L2 is a CFL, now if we assume this L1 L2 are complement or CFL, that will give us that L1 bar is a CFL. This is the assumption, suppose, and we will reach to a contradiction, and L2 bar is a CFL. Now, once they are two CFL, then we know their union is CFL. So, L1 bar union L2 bar is a CFL. Now, once these two are CFL, once this is a CFL, now we have assumed the complement is CFL. So, that will give us, this is a CFL, this complement. Now, this is nothing but the intersection, but we know the intersection is not a CFL. I mean, if we have two language L1 L2 which is CFL, their intersection need not be a CFL. So, that is the contradiction. So, the complement is not always a CFL, okay, because this property. But now, we will see another interesting property of the intersection. Although the intersection of two CFL is not CFL, but if we take one CFL and another one is regular, then their intersection is CFL. Like if we have two language L1 and L2, and suppose L1 is a CFL and L2 is a regular, okay, is a regular set, then that means then we can show that L1 intersection L2. If it is CFL, we know this is not a CFL. If L2 is CFL, then L1 intersection L2 is not a CFL. But if it is regular set, then we can prove that this is a CFL. Okay. The CFL is the, so CFL is not closed under the intersection, but once we take one language is CFL, another language is regular, then their intersection will be CFL. So, this proof we are going to just give the outline of the proof. So, basically what we know, if we have a if L1 is CFL, that means it will corresponding to some PDA M1, which is Q sigma delta of delta 1 Q0 Z0 Fn. Anyway, we have a M1 which is PDA, and for L2 we have a L2 is a regular set, then we have corresponding a DFA, deterministic finite automata M2, which will accept that. Now, what we do? We run these two in parallel. So, we will construct a new PDA where we don't have stack for this, but we have stack for this. So, we have a this is our DFA and this is our PDA, and PDA is accepting this stack. This is the top of the stack like this, and this is the input is going here, going there, and this we are XORing, and we are taking the accepted or reject. This is the AND gate, not XORing. So, this is the input. We are running this in parallel. So, and the stack is with the PDA only. So, this PDA will be running, and then once this is. So, this formal proof of this formal construction we will discuss in the next class. Thank you.